the first presentation under the title of Dissolving Pulp from Non-Wood Feedstocks, an alternative pathway towards the obtaining engineered sustainable fibers for the textile applications will be conducted by Mr. Ramon Vera. So Mr. Vera is a chemical engineer working as a pulping and product development research leader in the Sustainable Alternative Fibers Initiative, SAFI, at North Carolina State University. Besides hygiene, tissue, and packaging applications, his work on SAFI focuses on developing non-wood pulping processes to maintain fibers suitable for sustainable fibers, textiles. Moreover, Mr. Vera is developing strategies to upcycle cellulosic textile waste into value-added products at the heart of the circular economy. So, Mr. Vera,
thank you.
Please, the floor is yours.
Thank you so much. Yeah, I'm going to place my slides first. Okay. Okay, so good morning, everyone. I hope you can listen me well this morning. I'm going to be presenting today the obtention of dissolving pulp from non-wood feedstocks as an alternative pathway to obtain sustainable fibers for textile applications. So yeah, I'm going to start explaining a little bit about SAFI, what's SAFI, and then I'm going to proceed with different pulping alternatives that we are following to obtain dissolving pulp from non-wood feedstocks. And also at the end, I'm going to show you some products that we are making from that pulp. So what's SAFI? SAFI belongs to the Sustainable and Alternative Fibers Initiative developed in NC State University in the United States. And this is a consortium that is supported for more than 20 companies that are key players in the pulp and paper industry. So when we talk about non-wood feedstock, we are talking about essentially feedstocks like agricultural residues or even purposely planted crops that can be utilized as a feedstock for different pulping processes. So for that, we are developing different pulping strategies going from solvent, chemical, and even mechanical pulping processes for different targeted applications like tissue papers, dissolving pulp, and packaging. Today, I'm going to be focusing on dissolving pulp, but it's important to mention that dissolving pulp looks for having a pulp with high purity of cellulose. We are talking about cellulose with a purity higher than 90%. So another thing that we need to consider is like we want to decrease the hemicellulose content, and depending on the different dissolving and regeneration process, the content of hemicellulose can change. It's important to mention that there is some challenges when we are talking about non-wood, starting from the point that we have a very high content of ash, that in conventional pulping processes like craft, it challenged particularly the chemical recovery process. And something important regarding the dissolving pulp is like we are having a very high content of hemicellulose in these kind of feedstocks. So it promotes some operational problems, and of course the high content of hemicellulose challenge the obtention of dissolving pulp in this case. In this particular case, I'm going to be focused on sulfite pulping process, particularly because it has the opportunity to promote black liquor with lignosulfonates that can be utilized as a byproduct, and we could avoid the conventional chemical recovery process. It's a versatile process. Depending on the pH of the process, we can have multiple applications going from tissue to dissolving pulp. So regarding the utilization of the lignosulfonate and this liquor or spent liquor, we could apply even a circular economy where the lignosulfonate, besides many other applications, can be utilized as a fertilizer. So we can implement this circular economy in this case with sulfide pulping processes. And one of the types of sulfide pulping is the combination of sulfide with solvents, in this case the sulfur ethanol water pulping, or SEW. It's a very versatile process. We can have valuable and pure lignin, and also we could apply a biorefinery concept with this type of pulping. Okay, so we have the cooking liquid, particularly based on a charge of 10% of SO2. And additionally, we have played with different temperatures and time. And additionally, we have finished with an alkaline extraction and a bleaching process in order to purify the pulp at the end. So we have played with different conditions. You can see here that we have up to 12 conditions, pulping conditions. And we have tracked not only the yield, kappa, and brightness, but key properties in dissolving pulp, like viscosity and, of course, the chemical composition of the pulp. Particularly, the number 11 and trial number 12, you can observe, like, for example, is the highest purity in cellulose and the lowest content of hemicellulose in this case. So I'm going to be focused in these two conditions. So just to explore a little bit about what we have obtained, you can see that we have tried different pulping times, different temperatures, and you can see how the kappa is observed based on the time and based on the temperature. And particularly, you can observe here that both yield and viscosity, kappa can be constant at a certain point, but with a significant decrease in viscosity. And in this break point here is the key conditions in order to start having high purity of pulp. So this is something that you can corroborate in this chemical composition table. So we can start from the raw material, and from left to right, the pulping condition increase temperature and time. And you can see how the content of cellulose increase, as well as we have more strong pulping conditions, stronger pulping conditions. So particularly here we have a range of hemicellulose content, finishing with hemicellulose content up to 2.9%. But it still is not enough in order to have a high purity of cellulose. Remember that we need to be higher than 90%. And that's the reason why we apply post-treatment, like alkaline extraction or even bleaching processes. So again, I'm going to be focused on these pulping conditions. And this is what we obtain. So we start with the raw material, and at the end, we are going to have a bleach pulp with a high purity of cellulose. So now, in this table, you can see the two pulping conditions that we consider, and you can observe how the composition of cellulose and hemicellulose change after alkaline extraction, after pulping alkaline extraction, and after bleaching. So particularly for the pulping condition at 130 Celsius, you can see that at the end we can have cellulose content higher than 90%, but also with hemicellulose content even at 2%. But something interesting is, like, I'm going to be showing that, but when we compare with a benchmark, the ash content of 0.2% is still a little bit high. And this is what I'm going to be focused based on what we did in order to decrease a little bit more the ash content in this case. But before that, it's important to mention how we measure the dissolving pulp quality. And here I'm going to introduce the S10 and S18 concept. Particularly S18 measure the hemicellulose content in order to corroborate our comp analysis. But also the S10 can tell you the degradation of the cellulose in alkaline condition typical in the dissolving and regeneration processes. So here I'm going to make a comparison with other non-wood feedstocks in terms of quality. So we started with wheat straw. which it's been what I have been showing so far, this feedstock. So you can see we have a viscosity, brightness, S10 and S18. And when we compare this with a commercial benchmark, there is a close, it's a close quality compared to the benchmark viscose grades. What we are observing that we are having a little bit lower viscosity and higher S10 compared to the benchmark, which means that even when it's kind of close, we could have a similar quality compared to the benchmark in this case. So we compare other feedstock like switchgrass and hemp hurd. Wheat straw and switchgrass can have similar quality, but when you observe hemp hurd, particularly the S10 value is too high compared to the benchmark that we are making the comparison. So wheat straw and switchgrass are similar and can have a reasonable quality compared to benchmark, particularly for viscose grade. But for example, hemp hurd can have a low viscosity but still high S10. So somehow the quality or the potential of the feedstock to have a dissolving pulp quality depends on the nature of that. So here you have the comparison in terms of composition. So you can see that cellulose content higher than 90%, but particularly for hemp hurd is still high for some of the dissolving and regeneration processes. And regarding the ash content, we apply EDTA treatments in order to reduce. So in this case, we were able to go from 0.2% to 0.07%. Okay, so we have been able to obtain dissolving pulp with reasonable quality compared to benchmark for viscose grade, and particularly for wheat straw and switchgrass. Okay, so I'm going to finish with some product development. We are obtaining the pulp, and we are trying to spin fibers looking for textile applications. So the objective is taking the pulp and proceed with different spinning and regeneration processes. So for example, in this case, we are utilizing the carbamate fiber spinning. And of course, at the end, we are making the comparison with a benchmark, in this case, softwood. So we have the spinning process, the spinning device here. We have the conditions, particularly we are changing the concentration of the cellulose in the solution. And also, besides carbamate, we are utilizing anionic liquids, carbamate, and also a novel spinning and regeneration process based on fibrillation and suspension. And you can see that at this moment, we are obtaining fibers with potential to be utilized for textile applications made of non-wood processes. But not only fibers. In this case, we are also looking for acetate grade fibers and acetate films applications, particularly doing the acetylation of the dissolving pulp you are obtaining. And we were able to obtain acetate films with non-woods with similar quality to benchmark pulps. With that, the idea is to implement non-wood feedstock for multiple applications, considering textile, acetates, and even non-wovens. To finish, it's important to emphasize that non-wood can be converted into dissolving pulp with a potential for textile, acetate, and non-wovens. And besides, technically, it can be made. We need to corroborate the economics and environmental feasibility. With that, thank you so much. Thank you.
Okay. Thank you. Thank you, Mr. Vera, especially that you kept the temper. Of course, this issue, this use of natural fibers and the corresponding non-biodegradable synthetic fibers use will be a key issue in
Oh, yes. Thank you.
So now you have the second presentation under the title of Pulp Reactivity Assessment using cold alkaline solution in temperature-dependent cross-polarized light microscopy and dynamic scanning calorimetry. Mr. Antti Koistinen will be the speaker. Mr. Koistinen has a doctoral research is a doctoral researcher at the Department of Bioproducts and Biosystems, Aalto University, working in the Biobased Material Technology Group under supervision of the well-known Professor Ted Malone. His research interests are in the exploration of the dissolution mechanisms of cellulose fibers in a cold alkaline solvent, and how changing the fiber morphology and chemical composition affects the cellulose interaction with the solvent. So, Mr. Koistinen, the floor is yours.
Thank you, Mr. Chairman. Thank you so much for the organization for having me here. It's a great opportunity to tell a little bit about my research. I'm working at Aalto University, as mentioned here before, and I've been working with these things for the past some 3.5 years, and this is a really interesting field. So basically, I'm studying the dissolution of cellulose in alkaline solvents. In fields actually that are something like we just saw with by the previous speaker, to produce, for instance, spinning like fibers. You need to that's an important field, and it's especially in Finland it's something that is studied very intensely. Can you hear me at the back? Okay, perfect. Yeah. All right. So introduction. Let's see what is this all about. So to manufacture these regenerated cellulose products, as we just saw in the previous presentation, in the end, we need to first dissolve the cellulose because we cannot melt it. We cannot melt cellulose like we are able to melt several other polymers like polypropylene and these things. So we need to first find a way to dissolve it, to be able to then regenerate it in an anti-solvent. Okay, and cellulose is an amphiphilic polymer, so that means that it has both these hydrophilic groups like the hydroxyl groups you see over here, and it has a hydrophobic sort of backbone. So it's got both properties, hydrophobic and hydrophilic, and this makes it very difficult to dissolve in like regular solvents that we have around. So the solvent that we need to have to dissolve cellulose needs to be able to address these amphiphilic properties here. And one interesting solvent is aqueous alkali. So for example, sodium hydroxide in a water solvent. It can be used to dissolve cellulose under some very specific concentrations, 7 to 10% weight percent, and in near 0 Celsius temperatures. This is very interesting thing that it's got to do with how the sodium ions interact with the water molecules in this sort of form certain size of hydrates, which are able to disturb the hydrogen bonds between the cellulose molecules. And when you drop the temperature, the hydrophobicity of the cellulose is also disturbed. And and this together causes cellulose to dissolve in the solvent. It's very complex, and I've been trying to understand this. So and there's some consensus going on in the scientific community on how this happens, but it's still an ongoing field of research. What I've been studying is how we can modify the cellulose feedstock and to be able to dissolve it in this system, and it's called cellulose activation. So we alter the morphology, so how the pulp fibers like cell wall layers are formed and their composition. We alter that, and also we decrease the molecular weight, so we chop down the molecule to be smaller. So these sort of things are called cellulose activation. So that's needed to be able to dissolve the cellulose. And I've been developing 2 new methods for studying this dissolution phenomenon. I'm interested in the kinetics, how fast the dissolution occurs, and how completely it occurs. So these 2 things, and I will be talking about these 2 new things here, and so I hope we all learn something by the end of this presentation. These methods are, I'm using DSC, dynamic scanning calorimetry, and temperature-controlled cross-polarized light microscopy. And I will tell a little bit of these in more detail. The background is here that, okay, the cellulose dissolution depends on the feedstock and the solvent. Okay, that's what I basically said already. And each solvent has a certain temperature range. And for sodium hydroxide, the dissolution occurs around, 0 degrees Celsius. Okay? And if we control the cellulose solvent system temperature, we're able to dynamically induce the dissolution to occur. And with these methods, we are able to visualize this phenomenon in real time and see it. And I will show you how this works. So starting off first with this microscopy method. So here's a microscope. Here you can see this sort of temperature, thermal stage that I can control the temperature. And how this works is that crystalline cellulose has a birefringent property when you see it under cross-polarized light. It means that it, lights up. The crystals, I will show you this in a moment. It's pretty fantastic. And as the cellulose dissolves, these crystals go away, but the birefringence goes away, and you have in the end, just black image. And it looks like this. I am really sorry, my videos are not working. Let's see. We're going to have a lot of trouble if my videos are not working here. Excuse me?
How do you put the video? Do you want any help?
I sent it, can I use my old computer?
Yes.
Okay, thank you. Sorry about this, Mr. Chairman. I will just, use my own laptop. Take this off, please. So here we were. So this is what it looks like. So we drop the temperature and the cellulose dissolves and the crystalline domains, they dissolve, and in the end we have just blackness. And with the help of some Python programming or whatever, pick your poison, we're able to turn this into values. We can normalize it so everything is neat and starts from 1 and goes down to something like 0 if you're very lucky with the dissolution. And we can plot into beautiful curves that nearly fit on the screen. So this is something that we can use to turn this into something scientific. So here's what I did. I did just like a trial on, okay, let's do something interesting with this. I took pulp, regular Kraft pulp, and I used some acid to hydrolyze it, chop it down, activate it like I was talking in the beginning. I checked what's the, viscosity values with this, CED. They calculated the degree of polymerization from that. It's pretty, straightforward thing you can do in the laboratory. I used sodium hydroxide solvent with some zinc oxide in it. It's an additive that makes the dissolution a little bit more, easy. And then I did my research. And here's the DP is 1200 here, and over here on the right corner that's DP 200. So let's take a look how these different samples how they behave. So let's drop the temperature. This is sped up 10 times, by the way. So here we can see something happening over here on, okay, the DP 200, that's already gone. And the reference pulp that nothing had been, done to this one, it doesn't really dissolve at all. And okay, we reached something like minus 14 degrees here, and you can see that, okay, very fantastic. We have differences between these. So let's plot these curves. Let's do that again. So we're dropping the temperature at 10 Celsius a minute. And we can see in real time how the dissolution is happening, and then we can plot these curves from it. And okay, already we can see that, okay, if you the smaller degree of polymerization you have, the faster it's gonna dissolve, and more complete it's gonna dissolve. And And then, you know, between there and, you know, what we started off with, there's going to be something in between. And that's not all. You can also see that these are pictures before the dissolution and after. And here you can actually see these, see something interesting going on. I don't know if you can see in the back, but over here in the front row, absolutely sees this ballooning occurring over here. So we have no dissolution at all, and we have some ballooning. This ballooning is very interesting. It's a sort of form of heterogeneous dissolution. So it's sort of some parts of the fiber start to dissolve, but some parts, you know, don't dissolve at all. So okay, here we go. So here we can see a little bit better. So these balloons are very interesting, and it's been studied quite a bit, and it's caused by the cell wall layers. Some cell wall layers dissolve more better than the others. And if you're able to destroy the cell wall layers with your acid, whatever your activation method is, then the fibers will dissolve. And you will see this in the next ones. Okay, so next one over here, we have this DP800 in my sample set. Before dissolution, it looks like this, but after it, you can see that there's a lot of this ballooning going on, actually. And also this homogeneous swelling. Okay, so that's heterogeneous swelling. You can see this sort of, you know, bubbles forming up. But then there's like this one doesn't have this ballooning going on. It's just, you know, swollen up like that. So that's very interesting. These are things you can see with the microscope. And then the smaller you go in your degree of polymerization, the more complete your dissolution will be. That's something that we can see. This is actually something that is known for quite a while already. And after, okay, this is here you can see like a complete dissolution, so there's basically nothing. And also in the beginning it's quite, you know, fragmented, so it's, the fibers are, you know, broken up. Okay, let's move on. DSC, it's the same thing happening with DSC. It means that, okay, under the dynamic scanning calorimeter, what you can do is you drop the temperature, you have your sample mixed up in there. It's going to be an exothermic event, this dissolution. It's going to release heat. With DSC, you can track this heat. And basically the same story. And in the end, we can see these dissolution peaks occurring like this. The heat release can be tracked, and we can integrate this peak, and then you get a reading. Over here, you can see the samples freezing. The samples freeze, and, you know, there's a huge exothermic peak coming from that. No worries, do your thing. And then we can, you know, these peak sizes correlate with how well the dissolution occurs. And okay, here I have normalized the results by, you know, calculating as joules of energy per sample mass, or actually the cellulose mass in the pan. And you can see here that, okay, the reference that didn't dissolve that well, the energy output is on this level over here, but over here when you go to a lower DP, you get a lot of energy coming out. Of course, the story is a little bit different if you start calculating, like, you know, how many joules of energy per a mole of cellulose. It's a little bit more trickier thing, and that's something that we are trying to calculate in the future on you know, how to calculate that. So summary and conclusions of my methods here. So I've been working with these two methods here. With DSC and cross-polarized light microscopy, and, you know, you can see all sorts of things going on in there. When you drop the degree of polymerization, the dissolution is more better, and you can like get values out of that with these methods. And yeah, and this can be utilized to assess the reactivity rates of dissolution and also we'll be trying to use with different solvents as well. So okay, here you saw one solvent, but this basically works with any solvent basically. So you can use sodium hydroxide with different additives, but also ionic liquids. And yeah, so these are quite versatile actually. Okay, and that was basically it. Thank you so much. I want to thank my professor, Dan Maloney, for supporting this work, and I'm really happy to take your questions in the end. Thank you so much. Yeah, of course. Go ahead.
Now it will be better. So thank you very much, Mr. President. I think, despite the title was quite complicated to read, I think it was a really good presentation.
Thank you so much. Thank you very much.
So this last and third presentation will be done by Mr. Riku Kopra. So the issue will be using a process refractometer for measuring the performance of FIBERLINE processes. Mr. Kopra is an R&D scientist of Southern Eastern Finland, University of Applied Sciences, Fiber Laboratory, Savonlinna, Finland. Okay? Graduated from Tampa University and Applied Sciences as an engineer of paper technology in the year 2000 from University of Oulu, as a Master of Science in 2004 from Aalto University, as a Doctor of Science in year 2015. He has been published articles mainly about FIBERLINE processes as brown stock washing and O2 purification and wastewater system of chemical pulp, and present results in many conferences and papers. Recently, he focusing on air gases effect on the performance of oxygen purification and washing after by utilizing total dissolved solids measurements and bubble size monitoring systems and gas content measurements. So, Mr. Kopra, please.
Okay.
And the microphone.
Okay, thank you for introduction. Mr. Chairman, ladies and gentlemen, it's great honor and pleasure to be here. As Chairman said, today I will present for you study how we used process refractometers for measuring the performance of FIBERLINE processes, and mainly brown stock washing and O2 delignification. And here is contents of my presentation. First, I tell you words about the aim and target of the optimizing FIBERLINE processes. Then I tell the reasons why to monitor and control FIBERLINE processes, brown stock washing. Then I show for you measurement principle of process refractometer and also our measurement arrangement at the mill. Then results part and short conclusion. So, little bit background. We have done series of investigations to find solution that minimize washing loss, consume less energy, water and bleaching chemicals. And we have used process refractometers as measurement units and of course other data from mill's data collection system, wash water amounts, consistencies and so on. And today I will present study where we use these different measurements. Okay, as you know, brown stock washing has effect on many sub-processes like evaporation, O2 delignification, bleaching and wastewater treatment. And if we use a lot of wash water, chemical cost decrease, O2 delignification is working better, wastewater treatment is working well, but in the same time evaporation cost increase. So we have to find optimal operating point where all these sub-processes are balanced. And for that we need, if possible, online measurements. And here is listed few important key points what we have to think about when we are optimizing FIBERLINE processes. First one, wash water balance. We have to optimize dilution factor to maximize washing results with minimal evaporation cost. And you know that in the old mills evaporation is sometimes very limited, and we think about very exactly how much water we used, and then we have to wash brown stock washing very well. Then we have to optimize inlet and outlet consistencies to washers. we pretty often see in the mill that feed consistencies are too low, so we can get not good outlet consistencies, and then we lose some efficiency. And third one, optimize O2 states. That's also hard issue where we are doing a lot of research. Jari Käyhkö yesterday tell a little bit more about that. We have to, for example, think about amount of O2, alkaline, how to mix O2, what is the pressure, how much it can take washing loss, and so on and so on. And this my works concentrate mainly from this third. And then minimize carryover to bleaching and maximize black liquor trisulfuric content to evaporation. So, why we have done these studies and why we have to optimize and control brown stock washing and FIBERLINE processes. And motivation behind boosting FIBERLINE processes are mainly economic and nowadays also environmentally driven. And raw materials are increased also for industry. Energy balance should be a more important role in the future. And for example, in Finland, we try to use renewable energy, and 2021, 29.7% of energy was renewable, and food-based material was in big role. And as you know, this year Kemi mill started in Finland, and it's produce about 2 terawatt-hour green energy more. Then of course environmental issues. We have to decrease COD and AOX load to wastewaters, and then we try to increase profitable by making new bioproducts. Okay, then few words about our measurements. We have used process refractometers, and process refractometer indicates the total dissolved solid content by measuring refractive index and temperature. And it's not influenced by suspended solids, bubbles, vapors, color, and so on because of this measurement principle. And we can measure total dissolved solids in the filtrates, but also from the pulp stream filtrate fraction. So we can measure inlet and outlet concentrations and then do some calculations, for example, efficiency calculations. Okay, there is view of our measurement arrangement. On the left you can see that we installed 4 process refractometers to washers so that we can measure inlet and outlet stream and then calculate efficiency factors. We can change some driving parameters and look how it works. And on the right side there is a little bit bigger test in O2 telignification. There was quite many refractometers in the washers before and after O2 telignification. Then we have also 2 dispersion camera in the feed of O2 telignification and end of O2 telignification, and then we have also 2 gas content measurement. And for this setup we can calculate washer's efficiency, and we can also see what is going to O2 telignification and how much material is dissolved from pulp to the filtrates, mainly of course lignin. Then results part. Here is contents of my results part. First, one slide considering process optimization, how dilution factor affects the performance of washing, and how consistencies are doing. Then 2 slides considering O2 delignification, 1 slide considering whole wiper line optimization, and end of results 1 energy savings. Okay, then results, little bit paper with help. On the left we can see that when dilution factor, on the left we can see that dilution factor has clear effect on the washing performance. Then dilution factor should be above 1 to guarantee unembedded washer performance in this mill. But however, use of dilution factor above 2 is not feasible at this experiment mill because sometimes evaporation plant is a bottleneck. So TDS measurement can be used to monitor dilution factor, monitor the operation of the washer and the whole wiper line. And since available dilution factor is limited, it underlines necessity of efficient washing. And here is other results. We can see how washing consistency affects on the performance of a pressure filter. And we can see that if we have high washing consistency, displacement ratio is better. And so by changing operating parameters and monitoring the performance, it's possible to find optimal driving mode for the washers. Okay. Then we go to O2 delignification results. On the left we can see that if too much wash loss is coming to O2 delignification, kappa reduction begin to decrease because oxygen is consumed to oxidation reaction of washing loss. And on the right side, we can see that if we cannot remove air by flashing at over 100 degrees, and if this fails, cases may end up to next washer. These levels are pretty high, but the measurement is if pressure is moving or changing, it may be concern some mistakes, but we can see that there is a lot of changes, but levels are not so big. Then more O2 results. If we have a lot of washing loss going to O2 delignification, temperature can increase. And if temperature increase, it can be accelerate unselective reactions in the wiper, and we can lose some yield. And for this setup, we can measure how much dissolved material is going to reactor and what is happening after the reactor, and then we can calculate how much it's dissolved from the pulp to the filtrate. Then I show how we can optimize whole wiper line. There is 3 levels. Basic level, we measure what is coming to the wiper line, that's what is going out. And then second level, advanced level, we measure also what is going to and out from the washers. And completed level, we measure also what's happening in the O2 states. And then my last results, energy savings calculation. In this experiment mill, if we increase dilution factor by 1 unit, evaporation cost increase on average 1.5 euros per ton, and it makes about 900,000 euros per year in this experiment mill. And now you know that situation in Europe is pretty difficult and energy prices are going up. Of course, if we use more water, bleaching chemicals cost decrease. And there is short conclusion, maybe two first bullet is said, I say only this last one. The results obtained indicate that the measuring results of the refractometer can be used in various ways to monitor and control brown stock washing and O2 delignification. It's possible to achieve saves in the economy of the process in the consumption of chemicals. Okay, thank you.
Thank you, Mr. Kopra. It was a quite interesting presentation, and actually we are doing a similar job in our Navigator Pulp in Vera, and I believe that we already had some presentation during this conference. It was oral section number 5, as far as I remember. So we are doing a similar job, and I think it's a quite interesting way to follow the process. So now we'll have some time for discussions, about 15 minutes. Okay, we took more 5 minutes that was supposed to, but we can shorten the coffee period. So now we are open for discussion. So I ask the audience if they have any comments or questions to our presenters. Please, I ask that you make your identification and then proceed, please. Okay, okay, you need the same microphone. Okay.
Good morning, Joel Sansana from Navigator company. I have two questions for Mr. Vera. So the first one is, I know that you said that you didn't do the economic analysis, but do you have any idea that if using the black liquor as a byproduct, does it covers the cost of the energy consumption that now it's used by the recovery boiler?
Yeah.
So just the next question is, could you just explain more the S10 variable, because I didn't understand it. I thought it's a problem.
Yeah, thank you. Very interesting question. So, for example, in this case, in terms of economics, we are dealing with the production of lignosulfonates. Of course, we are not utilizing the black liquor for energy generation, but if you see the market for lignosulfonates, it can be between $500 to $800, depending on the degree, that somehow can mitigate the effect of not producing the energy on the process. So I think it's very promising, considering the black liquor or the spent liquor as a byproduct, particularly because for non-woods we are going to be dealing with small-scale operations. So yeah, and regarding the S10 and S18, these are key parameters in terms of, particularly for the viscose process. Probably you might know that the viscose process interact or make the pulp to interact with alkaline conditions. So for example, the S10 considers not only the hemicellulose, but also the cellulose that can be degraded at alkaline conditions, right? So that's the reason why that, for example, the S10 minus S18 is also a key parameters in order to determine yields in the process.
You know what, I had the same questions.
There are no more questions? Andrea, no questions? No question at all? Okay.
I have a question.
Okay. Finally, one question.
Good morning. This question is for Antti. So, did you show that one reaction that you think is dissolve pulp into the alkaline solution? But how do you know that the reaction is dissolution and not like degradation of the cellulose, like peeling reaction with the sodium hydroxide?
That's a good question. Excellent question.
That is a really good question, actually. And the thing is, with these methods that I have, we don't know. That's the thing. We can't tell. With the microscope, you can see that these birefringements that you have under cross-polarized light that is caused by the crystallinity in there and the crystals there, and that causes for that to occur. But we only see that the crystals go away. What happens, on a molecular level, we can't see that. And with the DSC, we see that there's an output of this exothermic peak that we see that. So there's something exothermic going on. So there's some sort of reaction that releases energy, and dissolution is something like that. But we also see this sort of exothermic event even with cases where there is very little dissolution. So also swelling that also occurs with sodium hydroxide and cellulose. So also swelling is something exothermic. So my answer to your question is that we can't see with these methods. So we are making assuming this. But the second question that I have is that does it matter that it doesn't actually dissolve? Because if we want to use it for spinning, for example, then is it okay that it's just something new form that we can push through a spinneret and then form some other material? And of course, from a fundamental scientific point of view, it would be fantastic to know that if it doesn't actually dissolves or not. But for practical, technical purposes, it's okay that it's that we're able to form some new material from that.
No other questions? There is one question.
Regarding the self-pulp, as the actual production of wood pulp is as we know, wood is a resource that we must provide, that we must protect. Regarding the dissolving pulp using non-wood materials, I think it's a good solution to have more cellulose here and having a circular economy. Do you have an idea of how big is the potential for that in terms of quantities? What's the potential for this product?
Thank you. Yeah, actually, very important question. At the end, wood is the main source of man-made fibers in the textile industry. It's important to acknowledge that. But regarding availability based on non-woods, it depends on the region. For example, if we go to the United States, from wheat straw, we have millions of tons per year of wheat straw. So, for example, in the U.S., utilizing the wheat straw for the dissolving pulp would have a very high potential. But yeah, at the end, it's going to depend on the zone where the non-wood is available. Availability is a key there. Mhm.
Not a question, just a comment. When we move from pulp and paper to other materials, we are moving from big quantities to small quantities. The overall business of pulp and paper is 400 million tons. The textile industry is 120 million. When I saw this figure for the first time, was just 100. And is 120 probably, and is 70% polyester. And the rest is basically cotton. So, and in this room and the other room, we've been talking about other alternatives, other things. Normally, when we're talking about other things, we come from this to this. And so, question of availability of wood will be more dependent on the policy that in Belgium, in Brussels, they decided than exactly what we are going to do, I think. It's just a comment, not any question. So.
So no more questions or comments? It seems not. So we can finalize now this section. So I would like, first of all, to thank to our speakers, of course, also to the audience. And now I have some final notes for you. So